Hey, I just want to say you guys are muted. Nice, thanks.
Fourth time's the charm. Hi, everyone. I'm hoping we have all the technical details worked out now. I'm still Matt Lease. I'm still from the University of Texas. I'm still very happy to be here. Thanks for having me. So again, at UT Austin, we have a large responsible AI initiative called Good Systems. This is a $20 million 8-year project that was launched by the president of the university, where our mission is design AI technologies that maximize societal benefit and minimize risk of harm. What is sort of different is a core tenet of our project is really that we think responsible AI can't be left to technologists alone, that we really need to have diverse expertise and perspectives involved. And just to give you a sense of the scale, we have over 120 researchers, over 31 departments involved. And we have what we call 6 core projects that we're really sort of focusing the work there. So I'm leading a project called Designing Responsible AI to Curb Disinformation. So our technical focus is on fair and explainable natural language processing technologies, with the application area of really using disinformation and societal needs around it to drive our work. So I'm not going to be talking about actually this today, but this is actually where a lot of my energy and time is going these days. And I'd sort of be remiss if I didn't mention the stuff we're doing in this space. So what I want to talk about today is some of the great work of my PhD student, Alex Braylon. Alex is one of 3 students I have who will be hopefully finishing this year. One is on fair and explainable, one is on sort of fair NLP around toxicity detection, one is on explainable NLP around fact checking, so sort of good system stuff. Alex has been doing work around annotation, agreement, and label aggregation, and I'll say more about this. But I'll be talking about these 3 papers in particular. We have a 4th JER paper that we just sent out the final version on, and I'll say a bit more at the end. So the roadmap for today, I'm going to talk about when we say complex labeling task, what is a complex labeling task? Why does it matter? What new challenges do they pose when we think about quality assurance and data collection? Particular two areas we're talking about is aggregation or consensus. How do we aggregate labels across annotators for complex tasks in order to improve label quality? And annotator agreement. How can we assess label quality for complex tasks via annotator agreement? So let's start with complex labeling. So here is a simple labeling task. We might ask, for instance, is there a penguin in this picture? And a common thing we might typically do is ask 3 people what they think the answer is, and then do something like majority vote. So 2 people say yes, 1 says no, and we think this is correct. And this kind of technique got very popular on platforms like Mechanical Turk, where we think that individual annotators might be unreliable, but in aggregate, they can be quite effective. So you see this sort of thing on lots of simple labeling tasks where, say, I want to label the sentiment, or again, classify an image, or I have maybe simple numeric ratings about Likert scale judgments or product reviews, rating relevance of search results. So in these kinds of tasks, we particularly first will think about this as objective labeling tasks, where we think there maybe is a right answer. And I'll say more at the very end of the talk about subjective tasks, where we think there's maybe a variety of valid opinions. But so we estimate both the label quality and the reliability of our annotators through basically this sort of popularity contest and sort of the extent to which they often agree with one another. So when annotators agree, it suggests both that the label is correct and that the annotators are reliable, or that the annotators share the same bias. And that's something else I can talk about. But what we assume is that if annotators are making independent errors, then we aggregate, those independent errors will cancel out. If they all share the same bias, then we're going to risk amplifying that bias. So that's another concern about when we apply these kinds of aggregation techniques. So then what's a complex labeling task? So imagine I ask someone to caption this image, and you might have one person says a cat is eating, another person says the cat eats, a third person says it's a beautiful picture. So every single annotator says something different. So with this kind of very large response space, identical responses are rare or they don't occur at all. And so typically trying to estimate annotator reliability or agreement via exact match is going to fail. And there are many complex labeling tasks. I mean, I should say a little bit more. There are hundreds and hundreds of papers about doing aggregation and consensus in the literature around human computation that are all based on this premise that you can check agreement on the basis of exact match. But there's almost nothing for these kinds of complex tasks. What people typically do is they build a custom bespoke model for every complex task of interest, which solves that problem. It's great, but doesn't let us solve the next problem that comes along, which sort of generalize very well across them. So whether we're talking about ranked lists, captioning, highlighting text, syntactic parse trees, lots of kinds of things like this where we have very large response spaces. Here are more examples. So doing key points of an image, bounding boxes, translation. So that's what we're talking about when I talk about complex labeling tasks. So aggregation, how can we aggregate this kind of stuff? So the first paper, this is my work, first paper my student Alex did back in 2020 was sort of what got us started in this space. So the key insight was that instead of trying to match things exactly, we could get partial credit if we had this idea of having a sense of how far apart annotations were. So if we could map annotations to distances between pairs of annotations, we could get all annotations could be reduced to sort of distance-based representation. So then we could model these distances between annotations rather than the actual annotations themselves. And the idea is that we'd want to exploit existing evaluation metrics that already exist for each task that you might use, say, to measure the distance between a gold label and a model prediction, versus use that already as an evaluation metric, which you could turn into a distance function pretty easily. So there's all kinds of distance functions that sort of already out there for these different kinds of tasks. The idea is that, again, for every task of interest, somebody's already made an evaluation metric to know how well you're doing. And then we can just repurpose that existing thing. So the way we get generality is we rely on the fact that the task-specific domains have evaluation metrics, and that lets us reduce everything to these distances. So here's an example. So here's our cat, and we can see some different annotations that people might give for it. So then we could measure the distance between their annotations, and you might see that these strings around the cat eating all have very small distances. So they seem close to one another, whether this one with there's a beautiful picture is farther away from the rest. So we compute those kinds of distances between all pairs of annotations, and we can do this for any of these different tasks. So we reduce everything to this kind of distance matrix, where we can see something about the distance between things. So once we have these kinds of distance matrices, how do we actually aggregate distances? So I'm going to talk about three techniques: local, a global, and then one that kind of puts those two together. And I'll describe them all using these pictures or visualizations on the right-hand side. So each box shown on the right corresponds to one item, one sort of instance I'm trying to annotate. And we're going to assume that the correct label is coming from the annotator whose face is green. So we're going to see something about how that annotator behaves both on the current item as well as on past items the annotator has done. And we're going to assume every item here is annotated by 3 people. So let's consider first smallest average distance. So we want to compute the average distance sort of, we want to figure out for each annotator how far their label is from all other annotators. And you want to pick the annotator who has the smallest average distance from anyone else. He's the one who's the most central. This is a local method because we don't look at all at the history. And this annotator who's most central in the current item may have been far from everyone else on all the past items. This is a generalization of majority vote for an exact match to this sort of distance space. So it's simple. There's no model you have to train, but it doesn't learn anything about sort of the reliability of annotators. The global approach, on the other hand, is going to say, look over all the data set and figure out which annotators tend to be most central. They tend to agree with each other most often on average. Then when I need to choose for the current item, which label, I'm going to pick the one from whichever annotator is most central on average. On the current item, they might be far away from everyone else, but I'm just going to trust that on average, they're most central. So maybe they're right on this one too. So this one doesn't take advantage of any of what's happening in the local item in terms of the current distances, but just uses this history from the past. So what we'd like to do ideally is get the best of both worlds. So can we sort of combine these together? And this is what sort of the rich history we have of aggregation models for simple labeling tasks does, is they combine both of these kinds of things. So we want to learn from this, but we want to generalize it to complex annotations. And so we need some sort of simple, some principled framework for doing this. So Alex came up with this Bayesian framework that was a generalization of multidimensional scaling. So multidimensional scaling has this idea of distance matrices. In this case, we're going to have a different distance matrix for every item, right? For every item, we can look at distances between all the labels for it. This is going to be a Bayesian version of this, and that's what's going to set it apart. And we'll have parameters about learning things like annotator reliability and item difficulty. So the first part of our model is just vanilla multidimensional scaling, which is the likelihood part of the Bayesian model. So you start out with the distances between all labels that are observed according to the distance metric. And you want to learn an embedding into a coordinate space that's actually going to make things as far apart in the embedding space as they are according to these observed distances. So in this case, these 3 labels we have around the cat eating should all be close to one another. So they're put in the embedding space close to one another, whereas the one that isn't is far away. So the part then where we start to bring the prior in, and this is where it departs from traditional multidimensional scaling, is where we choose this idea that at the origin of the space is pseudo-gold. That's we think the hypothetical correct answer is. And what you want to do is penalize the model for putting more labels far away from it. So all things being equal, the model wants to have more labels close to the origin. So we're going to basically translate the space. You want to preserve the relationships between items that we had through the embedding, but we bring the bulk of the labels closer to the origin, so the model pays less of a penalty for them. And this starts to look a bit like traditional majority voting. Now we have these reliability parameters we learn for each of the annotators. And what we want to do is further penalize the model for putting annotations from reliable annotators far from the origin. So again, if the label comes from a reliable annotation, we want to pull it from a reliable annotator. We want to pull it closer to the origin and move things around to make that work. So in this case, the annotator here with the lowest error, we're showing error with gamma, comes closer to the origin, and the ones with higher error get pushed farther away.
Question.
Yeah.
So I think like putting this prior for shrinkage at the origin, like intuitively makes sense. So could you tell us maybe what this coordinate system is? Like what are the X and Y axis? Is this an embedding space?
It's an embedding space, so totally latent.
Okay, and you just want to shrink to the origin.
Yeah, so we want to. So the high level idea, right, we start with is we think annotations that are very similar to other ones are more likely to be correct. We're not requiring exact match, but they're very similar. So we want to reward ones that are close to other ones. And that's what we get sort of with the first embedding that puts those close things together. But we also want to have this notion of reliability of the annotators. We want the reliability to also pull things that are more likely. So there's always this tension between sort of what do we observe on the current item in terms of who's most central versus what do we know about who's more reliable over time, and bring that together.
Just to be clear, it's not a semantic embedding space here. This is the space that you did the MDS on the distance matrix.
Exactly. And we do a different embedding for, you know, in some sense for every item here.
Yeah.
Okay, so in this study, the first one we ever did, we did the evaluation on 4 data sets. This journal paper we just finished up has tons of benchmarking on more real and synthetic, but the basic trends all hold. So we did this on 2 real data sets. One was text span annotation in biomedical text. Another one was an English Urdu translation data set. And then we had 2 synthetic data sets where we generated parse trees from a bunch of different syntactic parsing models and also generated like a bunch of different rankings. So in terms of evaluation, for each of these tasks, we're just using sort of the evaluation metric that comes from the task. So the same one that we're deriving the distance function for. And the first baseline, random user. So this is as if you just had one annotator do the task. How well would you have done to start with? So you just pick one annotator at random. We also have at the other extreme the oracle. Now, why isn't the oracle 100%? Because of the 3 or 5 annotators who did the task, none of them might have gotten it right. So the oracle is if you could just pick which is the best annotator, how well would you do? And I should probably just pause and make one point I should have made earlier in the talk. I think when we think about aggregation and consensus, we often tend to think about you're sort of merging the best between annotators, but almost this entire body of work that's been focused on aggregation and classification is this selection. We're just trying to pick the one label out of the set we got that we think is actually correct. So that's why the oracle here is just picking among the 5 annotators which of these labels is correct. I'll say more about that in this next section of the talk. So that's kind of where we are in the space between random user versus oracle. So there is this prior work in NLP called Zen Crowd, which is one of these ones which tries to learn reliability weights for annotators by when they agree with one another exactly. And in this large label space, we expect that to almost never happen. And so you think this model is going to behave like random. That's basically what we see. So sort of, again, the exact match doesn't happen. You can't learn reliability weights. We took one bespoke customized model for sequence annotation in particular. This was an ACL paper at 2017 by another former student of mine. So this was a pretty good, for that one particular task, you know, a very customized model made to do well on that. And then the last thing is our general model that I talked about with the embeddings. This is this MAS, multi-dimensional annotation scaling. So as you kind of expect, the MAS model doesn't do as well as the oracle, but does better than the random user. But I think the most interesting number here is the ones that are sort of shown in this fuchsia, pink, purple. We never thought this was going to do as well as a task-specific model, which was pretty surprising to us. Like the story I'll tell probably repeatedly, but I'll say here is, you know, our usual thought is, you know, if you really care about a specific task, you're going to go to great lengths to optimize for it. And that's wonderful, but it shouldn't be the first thing you do. The first thing you should do, ideally, is if you have a general model, try it off the shelf, see how well it works. And if it's not good enough, then invest the time. And that's what we were trying to fix in this work, was that you couldn't do anything unless you had a customized model for these complex tasks. So it's sort of remarkable that surprised us that it actually did as well on this, at least one task there. So overall summary of this summarized paper is these complex labeling tasks are really common, challenging. And even though we have like these hundreds of papers, and I told my students I don't want to do any more aggregation because I did a lot of this in the past. Alex found this place where there just wasn't any real general solution. And he's ended up doing this really interesting stuff as a result. So yeah, this prior work all depended on these exact match, which doesn't work. Having to design a custom model for every new task is a pain. And so we wanted to have kind of a general solution. This is the first that we knew of, and it gets around this issue of task specificity by exploiting evaluation metrics that are specific to tasks and then modeling those distances. And so yeah, we've been from the beginning and continuing putting everything online, open source with a permissive commercial license as well, so that people can sort of adopt this stuff in practice. So that's the wrap up of this paper. I think let me continue next for I'm just gonna have a teaser on the second one, and then I'll pause for questions after that before I go on to the last part, because this is still sort of aggregation. So this is a teaser because I wanted to make sure I had time to get to the agreement work at the end, but I just want to tell you a little bit about this stuff. I think one thing nice that Alex has done is each one of these studies has had sort of a key insight that kind of drives the rest of the work. And I think you can get these key insights across pretty quickly, even if you don't dive into all the details. So the paper I just told you about, one of the issues I raised was that we couldn't merge aggregation, we couldn't merge labels. And the typical problem is, I mean, let's see this for instance, you know, if we have some kind of complex label, if it's a bounding box, a parse tree ranking, whatever else like this, you seem to need to have some kind of custom way to merge every single one of these. So what we could do, what was great, is we could take any of these complex labels and we could pick the best one. But sometimes what you actually want to do is some notion like this, where you want to maybe average or merge them. And in fact, this is like the canonical example from the wisdom of crowds, is people guessing the weight of the ox, where you average all their guesses. So we didn't have a way to do that. The second limitation we had was we didn't have any way to sort of mix and match across annotators. And let me give you an example of this. So let's say, again, we have people say drawing boxes around penguins or something else like this. What we could do in the last work was we could just pick from one annotator all or nothing, their labels. What we couldn't do is say, I want some annotations from this annotator and some annotations, because we just, that wasn't supported. So what we'd like to be able to do is, for instance, imagine that the blue boxes here are the correct ones. You want to be able to aggregate across these two annotators and just pick the blue boxes at the end and not get stuck with one bad set of red boxes or the other bad set of red boxes. So those were the two limitations we were trying to address. So we had two insights here. So one idea was to take these complex labels and to break them down into smaller primitives for which aggregation operators already exist. And the inspiration here was actually serialization from sort of data structures. So if I take any data structure in my code, I can serialize it to and from disk, where I just decompose it into primitives and I know how to write those primitives out to disk. So could I do the same kind of thing of decomposition and recomposition of complex labels? So in this case, if you think about a span or a bounding box, there is a numerical representation, say the endpoints of it, or the corners or pixels or something else like this. And so what I could do is basically, decompose the complex label into some set of primitives, aggregate over each of the primitives, and then recompose back to the complex label afterwards. What's interesting here is the choice of primitive representation actually leads to really different aggregates at the end. So for instance, on bounding boxes, the first person who ever suggested this idea, we found something later on, had talked about just doing bounding boxes based on pixels. But if you just aggregate pixels, you don't actually get a bounding box at the end. So that was one sort of, obvious thing, is you have to pick the right representation that's going to give you what you want at the end. Another one that was sort of interesting is in terms of rank aggregation. So if you decompose rankings into the rank position and then aggregate those numbers, what you get is a very classic Borda-Fuse algorithm from the 18th century. But if instead of doing it by the rank position, you do the reciprocal rank position, then you actually get the Dowdle rank aggregation. So there's some of these things that your choice of representation, again, is going to change what you get in terms of the aggregation at the end. So there's lots of questions about how you pick what's the right representation or best representation to use. And then, of course, once you're in the primitive, you have a choice about, do you want to, for instance, do mean or median? And of course, median is going to be more robust to outliers. So I think that was sort of interesting for that part. The second thing is this mix and match business. So how can I get just the blue faces and the blue boxes and not the red ones that I don't want? And so the idea was to basically try to cluster which box corresponds to which underlying object and then aggregate based on those. So I'll show a better picture in a second. But so if we have single object, it's pretty straightforward, but what do we do with this multi-object? So this idea, and you kind of watch the top left picture, will annotate a little bit. But imagine you have the annotator drawing keyframes on this image. We have 4 or 5 different annotators. So you get all of these keyframes, And kind of what it looks like if you color them by annotator is the bottom left picture. You have this mess of all these different colors going on. So the idea is what we want to do is cluster, essentially. Can we cluster the labels together to figure out which annotations correspond to which underlying objects? If you can do this clustering, if you can partition the annotations, then within each partition, then you can just aggregate within that partition. And so we sort of solve each partition separately from the others. So what this needs to work, oh, I guess it's not here. What this needs to work is clustering. Clustering requires a distance function. Oh, wait, we have distance functions because we get those from evaluation metrics. So the success of this approach basically depends on how good you can do clustering. We did pretty crappy clustering when we did this work, good enough to make the point. There's definitely space here for sort of better clustering leading to sort of better outcomes. So that was the wrap up of this work. Again, was we had these two ideas that we could handle merging just by decomposing and recomposing through primitives, and that we could handle these multi-object annotations where we wanted to mix and match by clustering to partition, aggregate within each partition, and then you just have the labels that come out of each partition at the end for consensus. Okay, so this is probably a good point for me to pause and see if there's any other questions. I'll be talking about annotator agreement next. Yeah, so no, it's a great question. So definitely the work has spanned the gamut of between supervised, semi-supervised, and unsupervised methods. So the method I talked about indeed was 100% unsupervised. So the only thing we can learn about the quality of a point is how much you agree with one another. And when you have this kind of popularity contest, what you see is, and what's popular, you can't tell when somebody disagrees with the majority if they're the village idiot or the guru on top of the mountain who knows what everyone else has missed. And so we and others in sort of past stuff in the single labeling space kind of show that indeed a little bit of gold data goes a long way, because when you see those cases when you have an outlier, you can't tell if that outlier is good or bad without a little bit of supervision. So definitely bringing in a little gold is hugely valuable for that. And then, so when Alex did, I didn't mention it, he did the first paper in 2020. We had a semi-supervised technique that brought some of that gold in and showed some benefits. And in this journal paper we have coming out probably next year, he has a new, better semi-supervised algorithm for bringing that gold supervision in. So the usual thing, like we always think about with supervision, is if you can pay for the gold labels, they make things better, but you just have to pay for the cost of them, whereas the unsupervised stuff is free. So kind of the usual trade-off you think about with supervision. Okay, I'll continue on. Okay, so the most recent paper, we brought in Omar Alonso, who's now at Amazon. For those of you who don't know him, he's like one of the fathers of crowdsourcing. He's the one who got me into crowdsourcing back in 2009. So I wouldn't have done a lot of the work I've done in my career if not for him. And we were trying to find a way to collaborate for a decade before we finally made it happen. We just did some tutorials together before that. So Omar came on and brought a lot to this sort of work. So is there a penguin in this image? We've been looking at this before. How do we measure annotator agreement? So typically what we want to look at is something about the percentage of pairs that annotators match versus the percentage of pairs we might expect them to match by random chance. And there are many of these methods that exist out there in the literature you can take a look at. But it's back to this issue, what happens when we don't have exact match between labels? What happens when we have this sort of distances? So it's the same problem that we had before. Identical responses are rare, and essentially, those methods don't work. The body of the canon of literature we have around this stuff doesn't work. So one of the things we found was actually Krippendorf's alpha has a very general formulation I think most people don't even know about that actually can use these kinds of distance functions. But it has almost no study, and we'll see ways in which when we actually do try to apply it, it breaks down in ways that make sense when you look into it. So I'm going to switch examples and talk about translation for a second to try to make a point. So this is Japanese to English translation. I have 3 Japanese sentences, and for every sentence in Japanese, I have 5 English translations. And so what we're going to look at is The similarity between English sentences for the same Japanese sentence, where we expect them to be very similar to one another, versus English sentences that for different Japanese sentences, where we expect them to be different. So terminology, we talk about intra-item. Intra is sentences for the same Japanese sentence, and inter, sentences for different ones. So we have a color heat map, and we're looking at the distances between these sentences. And what you see kind of in this purpley range is the small distances. This is closer to the bottom of the color band on the right. So intra, the sentences tend to be kind of similar to one another, whereas the orangey is this larger distance higher up on the bar. These are the inter-item ones, so these are farther apart, which is kind of what you expect, right? English translations of the same Japanese sentence should be more similar to one another than two random English sentences. So observed distances that we observe, these are expected to be smaller, and bigger are these expected distances. So what Krippendorff's alpha does is it takes what's the average observed distance, I see, so the average one of these ones for intra-item, and divides by the average expected, the average distance over all these inter-items, the ones between sentences. Now, one question you have to ask that isn't answered really anywhere is what distance function do you actually use? This comes up for all the aggregation work as well, but it's particularly important here for agreement. So for any task, there's usually multiple evaluation metrics or distance functions. Does it matter? I mean, there's sort of a semantic question, just sort of fundamentally, what differences matter to you and what differences don't? So if you might think about something like language, you know, if I say car versus vehicle, those are different words. Is that an important difference? If I care about semantics, maybe not. If I care about lexicography, maybe it is. So there's some difference there that's kind of fundamental. But let's look at this just sort of more just from crunching numbers. So glue is a metric for evaluation. We're using, here's a distance function, and we're seeing over a larger number of English sentences here. Again, that nice kind of pattern we like. So it looks pretty purple there between sentences for the same Japanese translation, where it looks pretty orangey for these random pairs. Now, if I take a different distance metric called blue, this is an evaluation metric that was used prior to glue for evaluation. You see it's much more of a modeled picture there. It's much less clear that we're actually seeing smaller distances for the intra than for the inter. Okay, so what you expect then is a better distance function that's doing a better job pulling apart the intra versus inter-item distances should be rewarded with a better agreement score when I plug it into a metric like this. So good distance should show smaller distances for the same item versus different items. Oh, I just think okay, there we go. Question?
Well, you're assuming that the items are odd from each other.
Yes, that's a reasonable point, right? So if I think two Japanese sentences are very similar to one another, then their English translations would be similar to one another. Absolutely. So we've thought about that, haven't done anything with that yet, but on average, two random Japanese sentences you pick are going to be unlikely the same. That's an astute observation. Yeah. Okay, so better distance function should improve when we calculate our agreement measure. We don't see this with Krippendorff. So Krippendorff is actually saying that it thinks there is higher agreement on the left than on the right. So why is it that when we seem to have a better distance function, we're actually getting a worse agreement score? So I call this a tale of two distributions. So I'm going to show you through synthetic data on the right what's happening, because it's clear, although I can show you with real data also. So our intuition, when we look at distributions, observed distribution, we're seeing in this sort of bluish purple. The expected, we're seeing that orangey. The overlap is kind of this magenta-ish red. We expect that less overlap means higher agreement, right? If the observed distances look less like the expected distances, then people can tell these things apart. So clearly looking at the picture, you can see at the bottom, there's less overlap. There should be a higher agreement score. Both of these distributions yield exact same Krippendorff's alpha. And the issue here is if you look at, again, what Krippendorff does, it just looks at the mean of these distributions. So that's the fundamental flaw here in using a Krippendorff in this way. It can't tell apart two distributions that have the same mean. So we propose a couple methods in the paper, but the one that's simplest and I think clearest is just taking Kolmogorov-Smirnov test Great thing, you can just go into SciPy and use it directly. Isn't that wonderful? You know, we like to have our bespoke, weird custom software as academics, but here's actually just a general thing people can use. So KS is going to tell us, you know, the probability that two samples were drawn from the same distribution. So 1 minus it will give us the sort of this distance. And if we, just 1 minus it will give us the agreement score. So if we look at the distribution on the left, where we see that high overlap, we see it gets a very low Kolmogorov-Smirnov score, whereas the one on the right gives us a very high score, which is kind of what you'd expect. So let's look at a couple of examples of real data. So this is our Japanese English task, and I have 4 distance functions. So we've seen blue and glue already, and I've just told you that blue is better. For those of you in the NLP world, you'll probably recognize BERT. We have the rise of the Muppets in recent years. This is now before large language models, but so BERT is even a fancier one, better distance function, we believe. And Levenstein is just sort of, again, looking at these kinds of lexicographic differences. So we believe we've ordered these distance functions from worst to best. And so we expect that's what the agreement scores should sort of tell us. When we look at Krippendorff's alpha, we do see that Levenstein is worse and BERT is best, but it gets muddled sort of in the middle. It thinks blue and glue are actually lower. So again, what it's telling us is if we measured agreement using better distance functions, we'd actually think our annotators were agreeing with each other less, which is counterintuitive. When we use this Kolmogorov-Smirnov test instead, you see this nice trend like you would kind of expect to see. That, you know, if you're doing a better job measuring your distances, you can better tell apart the distributions and you get rewarded appropriately. Okay, one more example. This is from bounding boxes. So the count diff, this is the dumbest one. We're just going to count how many boxes does each annotator draw. The coarsest thing sort of we could think of for a distance function. L2 is we're going to measure the Euclidean distance between them. Intersect over union, or I always forget the other name. Intersect over union is kind of one of the most common things people still use for sort of bounding boxes. Or there is this sort of fancier version of this now, which I think is generalized intersection over union, if I remember. I can't remember. So anyways, again, the order from worst to best, left to right. So Krippendorff's alpha, again, we sort of see for L2, it thinks there is a higher agreement with L2 than with either of these fancier methods to the right of it, which is sort of counterintuitive. When we look at the Kolmogorov-Smirnov test, again, it seems to kind of show this trend that we expect the numbers increase. One sort of interjection to throw in here is when we started doing this work on agreement measures, we sort of found it was just how to evaluate an agreement measure is itself its own thing, which can be a little bit confusing. So, you know, what are the things you saw we did here in this talk so far? I gave you pictures and intuition for what to expect, and we looked at it visually. I said, I know that these distance functions are better or worse, and based on that, it should rank these distance functions in certain orders and doing that correctly or not. Another thing that people do is they'll take gold data, simulate errors, and you should see sort of the smooth degradation. All this is to say is actually just evaluating these agreement measures is itself a bit of a challenge, and still space is needed, work is needed in that space. So what we saw then was that there was only one annotator agreement measure we saw that we could even use on all of this complex data. The one that was done had been almost unstudied, certainly hadn't been benchmarked in any way before this. And when we did start doing this benchmarking across tasks, we saw it was pretty unreliable. So it's good that there is something. You can use Krippendorff, but it seemed problematic to do so. The great thing is you can just go to SciPy and run the Kolmogorov-Smirnov test out of the box, and it seems to work much more stable. I don't think I have another slide. So I want to say something more about, you know, there's still lots of stuff to do here because, like, typically, if you think about you're running a data collection or data annotation, you want to know an annotator agreement is good enough that you can use your data, right? I mean, that's what we often use these agreement measures from the past. So how do you know what good enough means? Well, you know, you look at a Wikipedia page for Fleisch Kappa or something, and they're going to give you some numbers. Those numbers aren't necessarily good, but they're at least numbers. They're giving you an idea about this stuff. it gets much harder in the space because what we're seeing is depending on the distance function you choose, that's going to change what numbers you give. And depending on the task you're running, that's going to change what numbers you give. So it's hard to know what's a right number for what's good enough agreement before you actually annotate some data on your task and look at it. We think this Kolmogorov-Smirnov number seems to be a little bit more reliable, than Krippendorf. But I think really that's still another space too, is just trying to answer that most fundamental task. How do I know if my data is good enough to use? So further reading. So this JERA paper we have coming out, it's a synthesis and extension of the first two papers. It's just about the aggregation work. We have a more better conceptual treatment of what we mean when we talk about complexity. We have another model we introduced for doing aggregation. There is stuff on this semi-supervised, and I swear I didn't pay her for asking the question about gold data earlier in the talk. Another thing Alex has tried to think a lot about, from a practitioner standpoint, is how do I even know if my aggregation is working at all the way it should? So really trying to design unit tests that practitioners could apply as sort of really sanity checks to make sure that things work reasonably. And then, as I mentioned, a lot more benchmarking on both synthetic and real data just to better understand this stuff. I think one thing I forgot to say there is what we want is ideally not have to run entirely separate code bases for different tasks, not have to run separate code bases for aggregation for simple versus complex. I can say, having spent a little time at Amazon now, every separate code base you have to run, right, takes effort for engineers to create and maintain. So we wanted this stuff to be a one-stop solution. So we took the same framework and we ran it on all the simple labeling tasks as well as the complex ones. And it doesn't do better on the simple ones, which it wasn't designed to do, but it does about the same. So you can just use his one thing for all of it, simple and complex. So we just wanted to be at least a one-stop solution for getting started. So I mentioned at the very start of the talk, this issue about two things that I said I mentioned at the end. One is subjective tasks, and the other is bias. So with objective tasks, we think there's a right answer, and we're trying to get annotators to agree on it. But what if it's more of a subjective task? What's your favorite color or something like that? Then what we might sort of think about doing is looking at what's the distribution of responses we see, and what seems to be a normative response. Where do we think that the tendency is in the response versus what do we see as outliers? And that kind of analysis might be interesting in social science. We're trying to think about when I have these kind of responses, there isn't a right answer, what's sort of normative in this space? Or in terms of just quality of my data collection, if this person is consistently an outlier every time, I could actually identify that and then pursue further. Is that an interesting different every time? Or somebody who's just rolling their head on the keyboard back and forth instead of actually paying attention to my survey? So I gave this talk at Cloud Research 21, which is sort of a social science thing. And I basically said, hey, we've got this hammer for trying to let you look at subjective data and kind of look at these things. Is anyone interested? And I haven't heard from anyone. But so I'd love to still partner if there's somebody here who wants to think about this kind of stuff for looking at subjective data. The last one on bias. So again, I said we know if we have biased data, then when we aggregate, everyone's just going to agree with each other. We're just going to amplify the bias. And so how can we detect that? So if you have gold data, again, as was suggested earlier, then I can get a sense of when I aggregate, am I converging toward or away from where I think the gold standard is? And that's how my measure of bias. Well, what does that look like when I have these complex tasks? Well, okay, I can go and I can say, okay, in the embedding space, I have this consistent vector in this direction away from gold. So I do see I have a consistent bias. What do I do about it? I mean, I could try to move back in this other direction in the embedding space, but there's no label there. Do I try to generate a label based on the embedding space where I'm in? Or maybe I just try to select whichever label is nearer to that corrected position. So both these last two bullets at the bottom are basically ideas we put out there, but we haven't actually done a lot with. And if people are interested in sort of either of those, I'm happy to chat more. Okay, so just to wrap up, I want to thank both sponsors, Alex and Omar, who's been really great, joining Alex's PhD committee, And last but certainly not least, I really want to thank the crowd workers. We depend so much on all their annotations for so much of our research. And they don't often get the credit and love they deserve for all the work that empowers our work. So thank you to all of them. And thank you.
Awesome. Thanks, Matt, for a great talk. So any questions from the audience?
Yes, my question is that, I don't think it's that, method works for generative tasks, for example.
I'm sorry, I couldn't hear. Generative tasks?
Yeah, so for example, let me story about something and then we make very large space of response.
Yeah. You have anticipated Alex's PhD proposal he's working on right now. So yeah, it seems like because indeed what's exhilarating and terrifying about the large language models is the response space is so wide open, they can generate anything. That seems very similar to what you've heard me talk about of these labeling complex labeling tasks with the large spaces. So we're definitely thinking about using his aggregation hammer and his agreement screwdriver in this space with large language models right now. And he hopes it succeeds so he can graduate. Should I call him Ian or?
Yeah, you can call.
I saw a few pictures.
So we have a recent work called Your Watch to Annotate Towards Better Models through Annotator Reputation. It's in collaboration with my advisor, Professor Radha Mukherjee, and we're looking to four subjective NLP tasks. And basically, we model the annotator to let the model to accommodate its prediction for the annotator. So instead of aggregating labels, because for some tasks like case detection, certain words or phrases might be harmful to specific ethnic groups. So we shouldn't really aggregate labels in those tasks. So instead of doing that, we just let the model customize its prediction based on each annotator. But we can chat more.
Sure, yeah, I mean, it sounds really interesting. So I wasn't sure what the question was, but I'll use this as an excuse to mention something related. So we're definitely doing a lot around sort of fairness and NLP, and that's where you might think you don't want the majority to stomp out a minority, for instance. So we had a paper at the web conference by another one of my students who's graduating this year, hopefully Shoma Gupta, where we were looking at when people use toxic language, there's elements that are sort of the same across demographic targets that are being different demographic targets, and place where we use sort of customized language. And if you just train a one-size-fits-all model, you learn to fit the language of hate that's targeted towards the dominant target group, but you potentially penalize the language of hate that's targeting the minority groups. So it's another one of these cases where we want to think about carefully both how we treat the data we collect in terms of when to aggregate and when not to aggregate, but also how we do the modeling in such a way that we're sensitive to the fact that different people might have different opinions, different groups are going to be targeted in different ways, and we can't necessarily build one model for every different group and have that scale, but we want to somehow be sensitive to that in our design. Yeah, happy to chat more, that'd be great. Wait, one important thing I forgot to mention. Alex is on the call, so if anybody wants to ask Alex a question, he's on Zoom and I can put him on. Sir.
I think it was related to your first statement. So, you're incorporating or considering the individual graders reliability in the model. And so my first question about that is, to what extent is that dependent on the number of ratings by each individual?
Yeah, so great. So our work is probably not different than any others in this space, which is that, of course, the more history you observe from somebody, the better you can estimate them. There's no free lunch in this regard. We all try to do things to make these models more robust in case of sparsity. But yeah, no free lunch. So absolutely, if somebody only shows up once and does something and you never see them again and you didn't have any gold for that task, you won't be able to do a very good job estimating their reliability.
I have a follow-up question to that. So in our own work, we experienced that there are some raters with a large amount of data whose quality of rating is low. They want to do things as fast as they can. On the other hand, there are some very high quality raters who do very small amount, but very carefully. And it also, looking at their level of expertise, we see like those who have higher level of expertise do less. That they value their time more or something, or do it more carefully. So considering these like independent measurements of the raters' expertise, the like how carefully they do tasks, I feel like that can affect the reliability for each rater. And it is kind of also dependent to the amount of data we collect from them. So how can we incorporate these different factors for each rater into the model in order to measure a better or more reliable measure of their rater reliability?
Yeah, so a couple comments. So one is, in these kinds of hierarchical models, you typically have priors to deal with sparsity like this. So if you know something about, say, how good you think annotators from a certain group are on average, you know, and you see very little, you observe very little from a given annotator, your belief about their ability will be very close to the prior you have. Whereas if you see more, then that likelihood observed data can overcome the prior. So that's one way to deal with this. Another thing I heard you say that's interesting is we definitely know that there are power laws that some workers do a lot of work and a lot of workers do a little work. That's really well observed. I haven't heard before this any consistent finding that better workers do less work and bad workers do a lot of work. That could be true. I haven't seen that as a consistent finding. So I wouldn't go just on sort of the frequency of their work to estimate something about their reliability from there. What was the last point I think to say here? Yeah, and then, right, and back to our point about supervision, where a little gold goes a long ways. So the risk you have here is if you're just doing this fully unsupervised, then you're going to have majority rule, which could be the tyranny of the majority, right? If the majority tends to be bad, or, you know, the majority is stomping out this person who really knows stuff better. So that's where a little bit of gold goes a long ways to help identify these reliable people and elevate them up. So you have to certainly use care in this like fully unsupervised stuff if you do have cases like this you're talking about. Or like, you know, my case where I said, you know, you might have 100% agreement, but they're all wrong because they all share a consistent bias with one another. Sure, I think I saw first, yes, please.
So, I remember that you mentioned in the final part, like all the subjective information, like I don't fully understand like which tasks should we relate subjective and
Yeah.
for the yeah, I just can't imagine like which where we apply this thing.
Yeah, so we talk about subjective versus objective often like they're binary black and white, and usually there's more of a spectrum. And we had a paper at HComp, I don't know, 2015 or something, talking about these sort of partially subjective tasks, but you can sort of imagine it extreme. If I ask you if the Earth is flat or round, you know, you probably think that it's round. There are some people who are still going to tell you it's flat, but they're a relative small minority of people. So you probably say that's a pretty objective question, right? If I ask you what's your favorite color, right? There you think there's no right answer, right?
Yeah.
So that's gonna be a fully subjective test.
Yeah.
So you have to think about kind of where you are in the spectrum between places. So if I take something like translation, there's multiple correct ways to translate the same sentence from Urdu into English. So it's partially subjective. But, you know, if that English translation has nothing to do with Urdu, like the semantics is lost, then it's probably not correct. So you can kind of sketch out, we did more in that earlier work, again, whatever this range looks like. So there isn't any easy answer, but you kind of have to come down to the end of the day is, do you think there's a right answer, in which case you want to arrive at it? If you think there is not a right answer, but a distribution of answers, bimodal, trimodal, some larger thing like that, then what you want to do is learn a distribution. And so you have to know something about what you think the domain is and what you think the correct or space of answers looks like.
Well, I think like for the this part, like, I understand that if you get a great, matter of the space, like for example, the annotation space, like if we can get the similarity of the two sentence or the distance of the sentence, like if we can get a good matter of that space, like we can, we can get the reasonably good, aggregation, is that correct, or?
Yeah, so the first assumption we're making is that you have some way to measure, like with an evaluation metric in a domain, say a prediction versus a gold answer. If you don't have any way to measure how good anything is, then we can't help you, right? So you have to have that to start with. And ideally, you'd have some notion of whether something is a good measure or a bad measure in that space. For aggregation, the first paper we talked about was selection. So what we can tell you is that the 5 people who did this will look at which of their responses is most central to all the others, and you can just pick that. So that was a selection-based approach. In the second paper, we had one where we could do sort of a bit of this merging, like merging the 5 together or doing mix and match. So I'll take, on the 3 bounding boxes, I'll take 1 box from this annotator, 1 box from this annotator. So that's what we got from the second paper. In the third paper, we said, given that, we could actually measure annotator agreements, how much our annotators agree with one another. So those are the things that we can do so far with this distance function, if you have it. And then other than the stuff that I mentioned that we'd like to do in the future around bias and subjectivity.
So do you try something like use generative model word embedding or take it down, like working, or like I saw the first, but I don't know like why you need to use that up and then apply it in another method, like why just use L2 or something.
Sure. So, like, what's one of the holy grails in natural language processing? We'd like to understand when 2 people use different words and they're actually talking about the same thing.
Yeah.
And so if I just measure like lexicographic Levenstein distance, you know, that is some measure of agreement, but it's pretty poor, right? It's just at the level of the lexemes. When I go to fancier semantic models that understand more about things in embedding space, then I get a closer sense of whether 2 people have actually said the same thing. And in this case, when I'm thinking about annotations, what I expect is that when 2 annotators are annotating the same item that has the same meaning, their annotations will have the same meaning.
Yeah.
That's what BERT score gets at. So that's why it's a better distance function for telling me how similar these 2 sentences are.
Yeah. So yeah, my point is like, have you ever tried like just the word event to vector, is that a good matter or not? Like,
I don't understand the question, so maybe I take it offline. But the multidimensional scaling embeddings we do for I think I can understand what you're saying. So yeah, so something we thought about is if you want to pick a specific task, like we will just want to aggregate language, then you could learn the embedding from that particular domain and use it.
Yeah.
And that's something we've talked about, but then we lose the generality, which is sort of the larger point of the work. So we might be able to embed, we might be able to aggregate better in that language space, but how's that going to help us with bounding boxes and rankings and all these other things? So we've chosen to stay general and let other people customize on particular verticals of interest. There was another in the back first time, but I don't know.
Yeah, just keep.
I consider you work in various criteria frameworks to like systematically learn something about like which parts of like a label or task or harder or more crucial. Like I'm thinking about like, you know, like in the case of translation, which is objective versus subjective, like it matters that you get some words right. It doesn't really matter that you arguably that you get other words right. And it seems like if you have like distances between different like translation methods and like some notion of primitives, you could like sort of like systematically identify like which ones are key. Like I'm curious if you like sort of talk about that.
Honestly, I'm not sure I understand. I mean, certainly we've done some bit of this where we decompose and look at sort of what happens when we sort of aggregate those decomposed levels. So for instance, you know, you might take 2 translations, and if you just look at the word level, you'll find that they agree on some words and disagree on others, and you can try to aggregate at that level. But I think we just rely on the distance function basically to know which parts of agreement matter, which parts of agreement don't matter between the two sentences. So happy to talk to you more offline.
Yeah, so one question that I had, just, I know we're over time. So one question was, so the first part of the part of your talk, so we have the complex labeling tasks. So one way that I think of complex labeling is an image. Let's say where a given person like would annotate the arms or the legs, separate bounding box for the arm, for the legs, for the torso, and so on. So, which is more complex than the task that you are doing with this one bounding box, because in this case, there is also the intra-user error variation, because the given user's errors might be correlated, right? But then different users labeling the same image, right? So there is the inter-user thing also, right? So I'm just wondering, like, if you have thought of maybe generalization of do like multiple bounding boxes, or like maybe the equivalent of that in for like text applications.
I think the short answer is no, and I'll be excited to talk to you more. I was just going to bring up, if I can get it quickly here. So, this is one when we're looking at key points. Again, I think what you're saying is for each person, an annotator is drawing a frame, skeleton frame in a certain way. And so I think what you're saying is when they do that task, they might have a consistent bias in how that annotator draws the frame.
Or the given person were to annotate different parts in the image.
Yeah.
Like the head. So you ask an annotator, label the head or multiple objects in the same image, like the head and the arms and the legs. So there is an error correlation in the way they do these things, because as Iman's question was, if people are very lazy, they want to do things fast. So the way they would label heads, slightly off.
Yeah.
So there is also the intra-person error, and there is also the interperson reliability.
Sure.
So it adds more complexity to the scenario that you're considering. But I don't know if it's even like if you have thought of it or.
I think the short answer is no. The way we typically think about annotator reliability, again, is if you had some gold, you could certainly see that besides other annotators of seeing how well, does that annotator have a lot of random noise or consistent bias versus a gold standard? That's one thing you could learn. Another trick that's sort of related is if you think about subjective labeling tasks, how do I know if my data is any good? So with objective, we can check against gold, but with subjective, there's no right answer. So the trick you do with subjective is self-consistency. Instead of inner item, instead of inter-annotator, intra-annotator, is the annotator self-consistent? So in their workload, you slip them the same task at some point later on and see if they agree with themselves over time. So at least if you don't have a gold standard, that's one way of checking if the annotator is at least self-consistent.
Awesome, thanks. So once again, let's thank Matt for a great talk. So I think, so Matt, after the student meeting in this room till 2 p.m.
Okay.
So I think one of you should lead him to his next meeting, whatever.
Yeah, so I want to just talk more about like our, because our is like recently archived. So we just started